Hello and welcome to the first of 3 videos that will tell you a little bit about the SPAN spectrograph, which is the University of North Florida Astronomy Club's instrument for dissecting celestial light and understanding a little bit about the nature of the object observed. The basics of this instrument are that it's a fiber-fed instrument which can be hooked up to the telescope, and then the fibers are used to guide the light into a tabletop box, which then steers the light towards a diffraction grating. And then once it's split up into its constituent wavelengths, the CCD camera captures that spectra, and then you have a raw image of the object now in its constituent wavelengths. You want to take that information back to the lab and then analyze that a little further. But we're not going to go into those details in these videos. This is just going to tell you a little bit about how it works, how to set it up, and then how to capture your image. Light enters the SPAN spectrograph, which stands for stars, planetary atmospheres, and nebula, through the diagonal fiber box piece here. There are 3 different fibers held flush with the focal plane of the telescope. You'll see here through the mirror. When you look through the eyepiece or look through here, you can see them very clearly. And the 3 different sizes are so that you have an option depending on what you're looking at for pairing it up with the correct size fiber. If you have 2 objects very close together, you might have to use a smaller fiber to get just one of them. Or if you have an extended object, you might capture light through all 3 at the same time. So in video 3, we'll talk about how to hook this up to the telescope. There's also an LED switch here, which when you're looking through the eyepiece at your field of view and it's dark outside, you'll see that one of the holes will light up red. And you'll know that that is the 100 micrometer diameter fiber core. Then the center one is the 205 micrometer diameter core fiber, and then the one opposite the red dot is the 365 micrometer diameter core. So you flick the LED on and off to see which fiber is which. You line up the object and the fiber of your choice, flick the LED off, and then record your spectra. So once light comes through this piece, it is led down through the fiber train and into the tabletop box. Light goes around in through the fibers and leaves the fiber array here with the 3 fibers held vertically. Then from here, light is diverging. The collimator, an achromat doublet lens, brings the diverging light into parallel rays, where then it is reflected off the blaze angle diffraction grating and split up into visible spectrum, which is then captured by the CCD camera here. So the first thing that you want to understand is that you should never touch the diffraction grating without wearing one of the cotton gloves. If they're not in here, you need to use Kim wipes, multiple Kim wipes, but that's not even ideal because you can still get some of the oils from your skin onto the diffraction grating even with Kim wipes, and that will ruin the surface. Any chemicals will ruin the surface. The only way that you can clean this diffraction grating is with a light burst of dry air. So you don't want to blow on it because you can even spit on the surface and ruin diffraction grating. So use one of these gloves if you're handling the diffraction grating or manipulating any of the mounts or the rotation stage knobs. And this is the dehumidifying element, which we'll talk about in video 2, how to make sure that that's operating effectively. So we have a method here for calibrating this instrument, making sure that everything is working properly. And there might be a better way to do this because this introduces a lot of uncertainty into your measurement. But that will be the task of you in the future to develop new ways to do this. As of right now, this is our method. So you take the green laser, the 532 nanometer laser, out of the center support here, and you place it into the putty molds on top of the fiber array. It's important to make sure that the laser is going directly down the optical axis. So you want to look on top and make sure that it's lined up with the fiber array. You can also use a level to make sure that it is going horizontally across the optical bench. When you turn on the laser, you will see that when you twist the collimator or the diffraction rotation stage, that there will be two dots that reflect back onto the fiber array. So you want to make sure that these two elements are perpendicular to the optical axis. So you twist each one until the reflected dot is in the center of the fiber array. And when you do that with the diffraction grating, it will probably be best to make sure that the rotation stage is set at 0, so that when you make movements with it, you'll know where you're moving to. The next task is to capture the first order diffraction with the camera. And when you have it just set up like this, you'll see that there's actually a little dot on the lens cap of the camera. And as you rotate this counterclockwise, it'll cycle through dots that will increase in brightness as you go through until you get a very bright one, and then all of a sudden the next one's very dim. That last bright dot is actually the 0th order diffraction pattern, which is simply just the reflected image of the laser. So if you then go back to the second to last bright dot, that is the first order diffraction pattern now shining onto the lens cap, and that is the one that this blazed angle reflective grating is ideal for, is the first order. So you want to move the rotation stage until that second to last bright dot, when you're going counterclockwise, is now on the surface of the camera lens. At this point, you want to go ahead and calibrate the instrument, and that will require that everything is in focus. If you record an image through the fibers of a gas lamp, which is what we would do here in the lab. Here we have a gas lamp set up, but you can get those from the astronomy lab. Or you can use a portable gas lamp instrument, which we don't have right now, but could be a good idea to get, so that you can actually do this in the field and not in the lab, and ensure that when you're recording spectra, you know exactly where this diffraction grating is set and what wavelength is falling onto the CCD. So when you are analyzing your object, you know how to properly label the absorption or emission lines. As right now we don't have that, so we actually have these labels on the camera lens that will give you a way to repeat the angle of the diffraction grating. So when you go back into the lab and you record your calibration images with the gas lamps, you can have the diffraction grating set at the same angle. So first you want to have the bottom pointing down on the lens cap, and then there are black lines going across the top of the camera lens. So you want to make sure the camera lens is set at infinity, and that all your black lines are lined up between the mount, camera lens, and the camera lens cap. And then when you turn on the laser, you'll move the diffraction, the first order diffraction dot for 532 nanometers, until it falls onto the first marker. At that point, the center of your CCD chip should have the wavelength which corresponds to hydrogen beta, which is the blue-green emission line from hydrogen. So when you do this in the field, you have a way to replicate this, and you know which wavelength is in the center of your CCD. Of course, there's a lot of uncertainty in that, but like I said, this is something that needs to be worked on and improved upon as you use it more. So then you set it up with the first diffraction order with the first dot, and then you record your spectra, which we'll talk about in video 3. Then, once you're done recording that portion of the visible spectrum, you move the diffraction grating until the dot falls on the second marker, and now the center wavelength should correspond to the red emission for hydrogen, which is hydrogen alpha. then you go ahead and record your object, and you can then put together those two measurements and get the entire visible spectrum. Now you know how to properly line up the optics in the spectrograph. The next task will be to ensure that you're getting a focused image. In order to do that, you need to have a gas lamp, either the ones that you can get from the astronomy lab or in the future maybe a portable one. Right now we have the ones that you get from the astronomy lab. So you have the lamp and then multiple tubes. Right now we have a hydrogen tube in here. We click on, we see that there's some hydrogen light. We take the diagonal with the end that would go into the telescope and place it next to the lamp. Then the light will go through the system as we have had it set up right now, and then you want to go ahead and open the Orion Camera Studio, which you can refer to the span manual on exactly how to do that, and record an image. Then you should see some nice circular emission dots. If they're not circular, then you need to focus something. And the first element to try to manipulate would be the collimator lens. If it's not at the right distance, it's going to stretch the dots into horizontal lines or vertical lines. So you want to loosen up the bolt and move the lens forward and backwards until you get a nice circular dot. If you can't do it with the collimator, then you want to then shift your attention to the camera lens. It could be that the camera lens is not held at the appropriate distance from the CCD chip. And you can adjust these screws, the four corner screws, to either move the whole thing away from the CCD chip or towards the CCD chip. It should be at 50 millimeters from the CCD chip to this red dot, which will have these springs compressed at about 11 millimeters. You also need to make sure that the focal plane of the camera lens is coplanar with the CCD plane, and you can do that by moving one or multiple ones of the screws in and out to tilt the camera lens. If at that point you can't get an image, then you have something else going on, and that's going to take you trying to troubleshoot this in a little bit more detail as far as to what is happening here that's causing you to not get an image. If you have nothing, or a good image rather, if you're not getting anything at all, then you might not have the diffraction grating lined up properly. You need to go back through with the laser and make sure that you have the first order falling onto the camera lens. And then once you do that, if you're still not getting an image, do fine adjustments and then do a loop of images with the software, and wait until you see something fall onto the lens. Once you do that and you have a nice circular dot from your emission line, then you're ready to go out into the field and record spectra. So refer to the next video on how to make sure that this dehumidifying element is working properly, because as you move from the cool indoors to the warm outdoors, you're going to have a steep temperature gradient, which is going to cause condensation on these devices. And more importantly, you don't want any chemicals or liquids on the diffraction grating. So you'll want to set this up first and then have that going while you're moving. So again, like I said, check out the next video and we'll tell you all the things you need to go out into the field and how to pack up the instrument and get out there and take some measurements.